Okay, guys, this is the session to help you and to discuss a little bit about your physics and chemistry practical. Okay, and I think the first question: when is the chemistry practical? Wednesday. So it's soon, right? Okay, are you all excited about it? Not excited about it. But how's your prelim? How's the prelim experience of doing prelim and all that? Good? Yeah. You got back your papers? Okay. Are you happy with it? Uh, okay. Why? Could be better. Okay. Yeah, I mean, we are always, there's always, when you look at the paper, when you look back at the paper, they will always find that certain things that we could have. It's not so much about what actually happens in the practical itself. After that, you probably think that you have answered a few things, right? But the thing is, when you look back at your own paper, you'll realize that you could have lost marks in certain areas. Now, that's the thing that we want to highlight to you, how you can work on that. Okay, but this session, we try to keep it a little general at the start, and then we go to a bit of specifics. Okay, all right. So the whole idea of scientific inquiry, right? I mean, you all know that. The whole idea, it starts with, to be curious about things. Why certain things happen. You all do physics as well, right? Okay, like why does an object falls due to just accelerates? I mean, somebody must have thought about it, right? And then that thinking, and then to think about the real world. And now today there are a lot of things that people do. Why are certain things happening like this, right? Why do certain like chemicals, why do they react certain ways? That kind of question. And that will lead you. So you have to ask question and then think about the problem. So that is a certain scientific framework, to think in a certain way. And then designing investigations. Now, as the chemistry and physics students, you're going to have a planning portion in your practical, right? So I want you to take a look at this. This designing investigation, right, is something that they start from fundamental, actually something that we've already been talking about since primary level. Talk about what's the, what is the thing that, what's the experiment that we can carry out? What's the independent variable? What's the thing that we change? What's the dependent variable? And how can we do it fairly? That means what are the things that we control? Okay, so that the investigation just focuses on changing that independent variable and measuring the dependent variable. So that fairness, are we doing the experiment correctly? So later on, there we will do a little fun activity, and then we'll talk about it. And it comes to the actual experiment, right? Once you design an experiment, think about it. When you actually plan an experiment, you do it in such a way that you also want to, somebody can actually follow your instructions so that I can carry out that experiment. Like you write out a set of things, and logically, if I follow what you have written down, I should be able to conduct the experiment, right? And of course, once we finish, once we are done with the experiment, what are we going to do? We are going to collect data. Okay, it can be an observation. Okay, like chemistry is a lot of observation. Of course, there's also measurement, right? When you do a QA and all that, for titration and all that, you're going to do some. Hi, come in. So all this data, okay, we are going to use that. Maybe we'll plot a graph, we interpret it, and come up with a conclusion. All right. So basically, what are we talking about? So whatever you just saw there, right? It starts off with asking a question, why things happen, and then that question leads you to make certain observations, and then form a hypothesis. What's a hypothesis, guys? What is a hypothesis? They've always been asking this since primary level, right? Hypothesis. What's a hypothesis? A what?
Prediction.
Yes, a prediction, a guess. That means what we think that how it's like it can be a somewhat logical guess of how things happen, right? Or what's the relationship? We have a certain idea, like for example, the most obvious one, the steeper the slope, the faster will the a ball rolling. Okay, I mean, based on our own observation, we know that if it's going to be steeper, it's going to roll faster. See, once you have that hypothesis, let's say they ask you to design a question, you have some sort of idea. And then with that, you will design and conduct an experiment. Okay, that's what we were actually talking about just now. And then you get the data, you analyze the data, and then you come up with a conclusion. Now remember, for all these scientific methods, right, whatever we do, it must be, the experiment must be reproducible. Okay, and the observations need to be consistent. Then only, they actually go on and on. They keep doing this and this, and that's actually how all the certain laws came about, certain theories comes about. Okay, through all these experiments. Okay, now let's take a look at certain things. Okay, let's just recap. Measurements of length, guys. We have where is the okay? Where do we use this? Okay, a meter rule, right? A meter rule. Of course, this is not a meter rule. This is a measuring tape. But what is the smallest reading on your ruler? It's the smallest reading you can get. 0.1 cm, right? 1 millimeter. So that is why we have the precision of the meter rule is given to 0.1 cm. Now, up to this point, some students keep asking, is it SF or is it DP? Okay, I think there's this question, right? Is it SF or is it DP? Guys, whenever we record a measurement, it will always be decimal place. Like a ruler, the precision is 0.1 cm. So if you're going to record it in cm, you will record it as, let's say, for example, you measured 10. You will not record it as 10, you'll record it as 10.0, with the units on top, right? So you cannot record it as 10. If you record it as 10, they'll minus that 1 mark. Okay? Because you're not following the precision. Okay? And of course, let's say you are going to record it in millimeter. Will there be any decimal place? Let's say it's, millimeter, no decimal place. Okay? So just need to remember the precision is based on the instrument. So for all the measurements, right? For all the measurements, it is going to be based on decimal place. This is what you call raw data. The raw data will always follow decimal place. Okay, I think the digital calipers is a bit more precise, 0.01 cm. Was there any chance that for your prelim they actually gave you a digital caliper or anything? Did it happen? Oh, they gave you a micrometer screw gauge, the digital micrometer. It was tested in the prelim? Okay, good. Your case, no. But since it was tested, that means you have to be aware. So how do you record it? You just record based on, I think even though it can read, I think now the instruments can read a bit more of higher accuracy. We will record it to 0.001 cm. I think that's what your school have taught you, right? Okay, so remember, that means you may be given that instrument. The good thing is it's digital. So you don't need to worry about knowing how to use it. Just put it there, whatever reading, you get it right. Of course, you probably have to check for zero error, but you can tell it now, right? So small matter. So yes, if you are given a ball bearing, a wire or something, what did you all measure? A wire. So the diameter of a wire. Both of you from the same school, is it? Okay. All right. So guys, so remember all recordings. Now, there's always, sometimes they give you 2 marks. They ask you for a reading, like for example, diameter of the wire. They give you 2 marks, right? The reason why sometimes you go and take a look at why you only got 1 mark is because you only put in 1 reading. Okay. So have you asked yourself, why did I get 1 mark? It's because you're supposed to actually take 2 or 3 readings. And what do? You must take it at 3 different positions of the wire. I mean, no point just taking the same reading at the same point, right? So you get 3 different positions of the wire, you take the reading and show your average calculation. And then, okay, the next question is the average, how many decimal place or SF should it be? When it comes to average, right, you follow the same DP as the raw data. Whenever you do average, the number of decimal place will be the same as the raw data. You should not give more, right? All right, so here's just an image of the digital calipers, and here is the digital micrometer. So I think you can see it. The first one is given in millimeter. The second one is also in millimeter. So it follows the precision. Okay. Right, this one, measurement of time. Okay, this one is important because it's quite likely that you probably have to do it. Whether it's a physics experiment or chemistry experiment, you are going to do some measurement of time. Okay, and can I just check, because different schools have different, they'll say you can record to 2 decimal place or 1 decimal place. What's your school telling you? 1 decimal place. How about you all? 1 dp. How many decimal place? You don't know? Huh? 1 dp. Okay. So there is a reason for that, right? Actually, your stopwatch can measure to 2 decimal place. Some schools, I know they'll say, just record what you see, 2 decimal place. Some schools will say 1 dp. So you just stick to what a school has told you. At this stage, whatever your school told you, you just follow that, right? That's the correct one. Because the reason is because they'll say because of human reaction time, we don't want to consider the second decimal place, right? Just follow that, right? Because later on in my sample, I use 2 dp because some schools will just record 2 dp, right? So as you can see, the precision is 0.01 seconds. Okay. Now, we're going to see a little bit of a simulation here, just to try out this. Okay, so guys, for simple pendulum, right? Okay, I hope everyone on online, you can see this pendulum oscillating. Okay, guys, normally when do we start taking reading? Let's say you have started this to oscillate, right? When will you start taking reading? Let's say you displace it. When will you start taking reading? Okay. Okay. Do you think passing in the middle or taking it at the end is easier? Normally, what do you think is better? At the end. Can you tell me why? Correct. Because at the end, momentarily it's stationary, right? Okay, so remember, this is probably the most basic kind of oscillation that you're going to get. Okay, measurement of time. But still, you want to get it right. You take time, probably like you let it oscillate maybe about 2 or 3 times until it's stable and swings in one plane, right? And then you start timing, okay? Now, how about taking measurement of length? I think maybe we can actually get the ruler to move. I think we click on the ruler. We can stop this. Yeah, thank you. Okay, you see, measurement of length, right? Okay, you can see the measurement of length, you see, is actually given as 70.0 cm. It's actually from the point of where it is, the point where it's oscillating, right? Till the center of the bob. Okay, normally they'll give you a bob, right? Unless they give you an object. So you should measure it to the center of the object. So that's the length. Okay, so whenever you make measurements, always to the center. Timing, okay, oscillations, let it oscillate for a while, and then take, how many oscillations do you normally take? 15 or 20 oscillations, right? So you follow the instructions and you take it. All right. think we can move to the next.
Mana? Someone should this?
Okay. Shall we do one? Okay, we will do one. Okay, guys, we're going to start timing. Okay, when it goes to 20 oscillations. Okay, let it oscillate first, and then when we start timing at, let's say, okay, can 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. All right. Mr. Mingi is very skillful. He stopped it just nice. Okay, 34.60. So you can record it in school. You can record it as 34.6 lah. You can record it as 34.6, or some schools 34.59. So that's the time for 20 oscillations. So of course, by right, you cannot just stop there. You should repeat it one more time, right? You should repeat it one more time. So now we have the timing, right? Time for 20 oscillations, 34.59. And then you can calculate time for one oscillation, you divide by 20. Okay, what's the answer, guys? 34.59 divided by, you all have calculator? Hey, later you all need your handphone. You all have stopwatch, right? Yeah, because we are going to do something. Those watching online, right? Hopefully you can see the activity that we are going to do. Not too sure whether you'll be able to see it fully, but you can have your stopwatch. So the timing here is there. For time for one oscillation, 1.7295. So the thing is, okay, if you are going to record it to, if your raw data is 2 dp, then this is 4 SF, right? So your time for one oscillation can be given as 1.7, okay, this one maybe 30. You can give it as 730, or you if you are recording it to, yeah, 30, yeah. And if you record it to if you're recording it to 2 decimal place, right? Oh, sorry, 1 decimal place, then 3 SF, so it should be 1.73. Correct, right? 1.73, right? Okay. So we will take a look at it. Don't worry about this. Okay. This is just based on our reading here. Okay. Just a sample, right? I think we can go to the... Okay. So remember, guys, when timing oscillations for pendulum, repeat timings and calculate the average time, record time for a large number of oscillations and find the period. Okay. Start timing only after a few oscillations, and make sure oscillations are in one single plane. And the point that we said, right? Start timing when it starts to oscillate from one end, either end. And most important, guys, you know, during exam, we might forget. One full oscillation is to go from A to B and back to A. Okay, that's one full oscillation. Of course, just now I was counting loudly, right? In the exam, you can't count so loudly. You cannot distract the other person, so you have to count, you know, within yourself, right? Okay, all right. So other things, okay, let's go to the other ones, right? Okay, measurements of mass in kilograms. So most likely, if you're going to measure like chemistry, right, the lab, you probably have to do some measurements using the electronic balance if you have to take some reading. So probably in grams or what. So make sure you look at the digital display carefully. The unit for weight is Newton. Okay, if you're going to measure, guys, it's quite likely they might even give you a spring balance. Okay, a lot of these experiments come before. Okay, spring balance, and then you hang a weight. Okay, take note of it. Okay, what is the measurement, right? And when it comes to measuring volume of a liquid, whether it's using a burette, okay, or measuring cylinder is the lower meniscus. You read the lower meniscus. Okay? Okay, all right. So our measurements of temperature should be recorded to how many decimal place? 1. Yeah, 1. And most of the time is 0.0 or 0.5. 0.0 or 0.5, right? So you either record 0.0 or 0.5. Okay? I think it's mostly like this, okay? Okay, when it comes to heating a liquid, make sure you use a stirrer. Okay, I mean, these are all things that you've been taught before. To ensure that the liquid is heated uniformly and the Bunsen burner is completely, the air holes are closed before lighting. Okay, and the temperature of the Bunsen flame adjusted according to the size of the air hole, right? You all know this. Okay, all right. For those watching online, right? Okay, maybe you can't see this activity fully, but I'm going to show it here. Okay, coming back to our planning question. Those are here and those online, guys, think of the planning question. Okay, this is the thing that I'm going to tell you. Imagine you're asked to plan an experiment such that you want to investigate how terminal velocity is affected by the mass of an object. How terminal velocity is affected by the mass of an object. Okay, so for that, right, we're going to investigate the fall of a coffee filter. Okay, so the instruction here, guys, it says drop a coffee filter from a height of 1.8. Okay, I just realized 1.8, actually, the higher it is better, right? I mean, it's going to be like, there's going to be a lot of human reaction time, right? 1.8, the best is 2.5, 3, but I think we can't reach that. Okay, so I've already set this. Okay, I'm using, okay, I use this, okay, and this is about 2 meters there. So I already put a tape there. So this marking here is my 2 meters. Okay, just think about it. If I were to drop this, guys, you can get ready your stopwatch. Okay. Okay, this one is just to. Are you all ready? Ken, you sure you'll get this? Okay, when I release it, okay, I'll just put it up here. When I release it, you all start. And then when it hits the ground, you have to stop. Ready? Ken, what's the timing? Huh?
You do the second time.
I'll do the second. Of course, I'll do the second time. Don't worry. But anyone got a reading? 0.69. How about you? 0.35. Wow, so good idea.
Oh, I
Didn't impress. Okay, let's try again. Okay, ready? 1, 2, 3. 0.43.
We have some values online also.
Oh, online also got.
We have some
Oh, not bad.
39.
Was I blocking anyone?
They can't see the ball on the ground anyway.
Oh, yeah.
That's all they can see. They can't see the ball on the
Oh,
ground.
yeah,
How did they
yeah.
calculate when they cannot see?
But not bad, lah, not bad. Okay, guys, this one is challenging, right? This one is challenging. Okay, so that's why we are going to do with coffee filter. Okay, now it's a little more easier, right? And you know what's the beauty about this coffee filter, right? It's like the parachute. Actually, I actually thought about it. Why it can't fall this way? There's a reason for it. It doesn't fall nicely this way. But when you drop it like this, right, it falls very nicely. Okay, right, guys. This time around, okay, let's go. Everyone ready? Okay, those online, You can imagine where the end is though. Okay, 1, 2, 3.
1.2.
What do you get? Okay, 1.28, 1.32. How about you? Okay, 1.32. Okay, that's for one coffee filter, right? One coffee filter. Okay, now we're going to try with, okay, so we can take note of the
Did you
idea.
do it twice?
Yeah,
I'm taken 1 and 2, right?
yeah, but shall we?
I don't know what's your intention.
Because anyway, the three people taking, so I'm just taking their reading. So 1.32, is it? Okay, shall we do it one more time? Okay. Okay, guys, we'll do one more time. Ready, go. What do you get? 1.35. 1.34. Okay. Okay. Can? All right. Now we try with how many filters? The next one is 3, is it?
3 and 5.
Ah. Okay, guys. Those at home, now we're going to do with 3 filters. Okay. Ready? 1, 2, 3. 0.84. Buddy. Wow, so good. 0.84. Did you get? 0.82. Okay. Not bad. Let's try again. Oh, those online, not bad. How do you all see the bottom? Can see the bottom. Okay, guys, try again. Okay, 1, 2, go. Actually, by right, I shouldn't say 1, 2, go. You should take it when it leaves my hand. Correct? Shall we do it again? Okay, right, try. It's more for the online people. Okay, 1, 2, go. What do you get? 0.75. Any reading? Shall we do it one more time? One more time. Okay, one more time. Go. 0.95. I think maybe it's because I didn't drop it very well. Yeah, there was something wrong, right? Okay. Okay, 1, 2, 3. 0.73. Okay. Okay, now getting okay, you realize this reading by right should be
Majority
quite
says
close.
74. Majority says 0.74.
Oh, not bad. So maybe 0.74, but originally y just now was off by 0.1 second. Okay, guys, now I'm putting 5. Okay, I'm putting 5. Okay, 5. Okay, everyone ready? So what do you think will happen? You kind of will have some guess, right? Now that I put 5, what do you think will happen to the time? So you kind of expect it to be shorter, right? Okay. Okay, look at that. Ready, everyone? Now it's 5 filters. 1, 2, go. 0.63. 68.
Oh, but do it properly.
Didn't do it properly. 63, 0.63. Okay. Okay, Session, yeah. 0.59, yeah. So around 0.6. Okay, I'm going to one more time. 0.63.
5.1. I think.
5.1.
Hey,
Okay, 5.1.
yeah, 0.51.
Okay. 0.1 seconds.
Okay, okay lah. I mean, okay, so you can see there is a trend. I mean, by right, these experiments, right, you can see the first one with the first filter, you look at the timing, 1.32, 1.35, because it's a bit longer. We are very close to it, right? But as you can see, that after that 0.8, the human reaction time starts to come in, you know. Can you see? The human reaction time is about 0.1, 0.2 seconds, depending. So the factor starts to come in, okay? And then we can work out the average time, right? So average time is just you add up both and then you divide by 2. So this one, okay. So when you do the average, you round it off to 1.34, okay? So the 1.34 and then the other one will be 0. What is it? Yeah, 79. Yeah. And then we round it off to 2 decimal place. So guys, now at this point, right? Okay, so what is our, first, we didn't ask about this. What is our independent variable here? What's the independent variable? What are we changing? Number of filters, right? We are actually changing the number of filters. Okay, and what is the dependent variable? What's the dependent variable? What are we measuring? The time taken, correct? The time taken for the filter to fall from a given height, right? Okay. Okay, let's say, you know, for your physics practical, right? The planning question, it's always like this. They actually give you an experiment. You start off, you just do a little bit of experiment. Then they say, okay, from here, plan an investigation such that you study how terminal velocity, you know, you want to find out about terminal velocity is affected by the mass of the, let's say, the filter. Okay, so remember the question, they want you to plan such that it's based on, you have actually done a little bit of an experiment, but now they want you to be more focused. They say that, okay, how terminal velocity affects the, how the terminal velocity is affected by mass of the filter. So you see here, when I dropped it here, right? When I dropped it here, does it actually first reach terminal velocity? Does it immediately become terminal velocity when you drop it? No, right? Immediately not terminal velocity, right? So how will you modify this experiment? The experiment is still the same. Just that how will you modify it such that, you know, at least you're looking at a good chance of it having reached terminal velocity. So I dropped it from 2 meters, isn't it? Where do you think roughly you probably reach terminal velocity, especially for an object like this? But one thing you know for sure, you cannot take it immediately, right? So in your experiment, so the thinking part is, you probably say, you start timing when it drops to the, you have a lower mark. You take a reading of from the 1.5 meter mark. It's most likely could have reached terminal velocity, right? So instead of taking timing from 2 meters, you just modify it such that it takes from the 1.5 meters. That's one. And then how are you going to determine terminal velocity? You already have time, right? So velocity will be just the distance, 1.5 meters, divided by the time. So you have your measurement for the dependent variable. And of course, the mass of the filter, you just have to go and put it on the instrument is the electronic balance, right? You measure it. So, and what are the factors you control? You probably control the height from which you're dropping. Okay. That's one important factor to control, right? From where you drop. So all these things are actually, see, what we just did is just an idea of a simple experiment. And then you look at the data. That's why you don't need to worry about it. When you plan your experiment also, you just have to know what they're asking. Now, one last thing, right? It's about the relationship. They might say that the relationship between terminal velocities, you know, for planning, V squared equals to Km, something like that. V squared is related to Km plus C or something like that. So you are supposed to go and say that I will determine the terminal velocity, and then I'm going to, you know, all the processes, like how I measured the length. You know, you have to talk about the height, what instrument do I use, all this, you talk about your processes, right? How I measure the time, how many times I repeat it, then how do I work out the terminal velocity? I take the distance, divide by the time, all this, right? And then finally, V squared equals to Km. So you can say that I'm going to expect a graph where I'm going to process it such that based on the terminal velocity, I change it to calculate the terminal velocity, I change it to V squared. Correct? Change it to V squared. I process V squared and then plot a graph of V squared against M. And what's the trend you're going to get? So since it's related to V squared equals to Km, and the K is like the gradient, right? So you can expect a straight line graph if you plot V squared against M. So this is what your planning question is going to be like, right? Just an idea for all of you. Okay, I think roughly you can comment on the data. You can see that based on the number of filters, the more filters you add, the timing becomes shorter, right? Okay. Okay, now just a question, theoretical question. If the filters or any object, whether it's an elephant or an ant, I think you may have seen this in the actual video, right? Whether it's an elephant or ant dropped in vacuum by right should fall at the same time, right? Okay, you all have seen the video of the bowling ball and the feather, right? So they do it in a vacuum chamber, isn't it? They drop it, both will actually fall at the same rate. So technically it should. But what you saw here is actually an experiment investigating about air resistance, the effects of air resistance, okay? That's why you have different rates. Okay. All right, guys, this is a part all physics students or even for chemistry, right? Physics, you cannot run away, guys. You have to plot a graph. Your third experiment is all about plotting graph. Okay, so when you plot a graph, it's actually to show the relationship between the independent variable and the dependent variable. Now, plotting graph, I think you collect the data is one thing. Do you realize that it will take you some time to think about what scale to use? It takes you a while to decide what's the scale, right? Because it's easy for me to tell you, guys, choose a good scale. 1:1, 1:2, 1:5. But only a person with the data there will have to look at it for a while, to decide what's the best scale, right? When you look at the data. Now, remember, you don't really need to start from 0, 0. Okay, now some students ask, if I don't start from 0, 0, do I need to put anything funny? No need. You can just start, like, for example, you start from 20, 30, 40, say something like that. You can just start at 20. You don't need to go and put any zigzag or anything. You don't need to do that, right? Okay, so when you plot the graph, right, guys, remember a good scale ensures that you cover at least 2/3 of the graph paper, both X and Y axis. It should cover 2/3 of the graph paper. Okay, and don't forget to label your axis. Okay, you must label your axis. Okay, the Y axis with the units, the X axis, and the point should be marked clearly and accurately. Okay, long, transparent, guys, bring your 30 cm ruler. Okay, always use the 30 cm ruler, right? The transparent one. Don't go and bring the short one, okay, and flexible one. So that if it's a curve, you can use it to just draw the curve as well. Remember, it should be one single line. You don't stop and draw. It should be one single curve. Now, a lot of students, they worry, best fit line, can it be a curve? Yes, it can be a curve. Okay, they have asked a few times, it has actually been a curve, right? Okay, a best fit curve also can get it. Now, of course, make sure you have the right pencil. Okay, when you determine gradient, right, you draw a large triangle. Okay, and it should cover more than half the straight line. Okay, and guys, do not use plotted points as your gradient coordinates. And read the coordinates of the gradient. Okay, all working of calculation of gradient must be shown clearly. Okay, let's take a look at this, yeah. Okay, what do we mean by best fit line? This part, I think all of you know. Okay, just look at this. You have seen this before. Okay, the plots are there. This is definitely not a best fit line because why? All the points, your best fit line is trying to just connect the first point and the last point. But all points are shifted to one side. Okay, they are scattered. I mean, they are not balanced. The scatter is not on either side. It should be a balance. So look at this. This is your best fit line. Okay, it's the same points, but now you draw the line such that it's a balanced scatter on either side. Remember, a best fit line does not even need to pass through any of the points. Okay, some students think that it must pass through the first point and the last point, first and the last plot. No. It's as long as there's a fine balance of scatter of points on either side, that's good, right? Okay, guys, we take a look at the sample data here. Since we have been talking about oscillation, now for those at home, watching online, same thing. We have been talking about the length. This is actually data from simple pendulum oscillation, right? Now, I repeat to you again, if your school has been teaching you to record to 1 decimal place for time, you follow that. Some schools follow 2 dp, so I'm just showing you based on 2 dp. But if it's 1 dp, you just record to 1 dp. Now look at that, the units, okay, my length, 1 decimal place. My time, I follow consistently based on decimal place. My average also follows the number of dp of the raw data. Where is my process data? My process data is actually the period and t squared. T and t squared are the process data. Now, I repeat, if you had recorded, guys, some of you are just recording to 1 decimal place, right? If you have recorded to 1 decimal place, then all this will be 3SF only. Correct, right? Because now my data here is based on this. So now it's 4SF, right? But if you have recorded to 1 decimal place, all your raw data will be 3SF, right? So you'll follow 3SF. Isn't it? Okay. So you follow according to your raw data. You have to process and record based on your raw data. If your raw data is 3SF, your process will be 3SF. If your raw data is 4SF, it's 4SF. Okay. All right. So the first part is to actually plot the graph. Okay, guys, take a look at this. Okay. Try my best to show you the smudge of the graph. Okay, look at that. Both the axes were not started at the 0 mark. We didn't start at the 0 mark. Okay, the x-axis starts at 10, 20, 10, 30. So what kind of scale is this? This is 1:1. How's the y-axis? It's 1:2. 0.8, 1, 1.2, 1.4. So it's a 1:2. Okay, we are jumping at 0.2, 0.2, 0.2. This one jumps in tens, which is actually 1:1. Okay, right. Next thing, you look at that. Look at the gradient triangle, right? Okay, the gradient triangle. First, I don't go and choose any plotted points. I don't choose plotted points for my gradient coordinates. I just choose any 2 points which are, and the triangle is very big. Okay, the triangle is big. And then I write down the coordinates. Okay, so the coordinates here, okay, the x and y, the x and y. All right, guys, look at that. A few things to note. Labeling the axis, t squared, second squared, length cm. Now, I put myself where you are going to be inside the lab, right? When you do it, the part that's going to take you a little while is the deciding the scale. Once you got all your table right, you need to take some time to decide what is a good scale, right? Okay, I put myself there. Okay, that is the one that will be a little challenging, right? But other than that, once you take some time, do it, right? Okay, decide what is a good scale. Then you can come up with it. If you just quickly rush, right, you might end up with the wrong scale such that you don't think carefully. You may think the scale may be good, but I mean, you are using 1:1 or 1:2, but you might end up such that, you know, all the points are squeezed. The whole idea is the graph, you see, occupying 2/3 of the grid. Okay, guys. Okay, just to quickly, can you guys calculate the gradient based on the data given there? Those, you also have the same document, right? Yeah, those online, can you guys also work out the gradient? If you have any questions with regards to this, you can ask, yeah? Now, remember, I just want to highlight one thing. Very likely you will get something on electricity. It's quite common, they will ask. Okay. Now, the thing is, electricity experiments, you will you follow the instructions, you set it up. It can be a long question. It can be one of the smaller, it can be like either question 1 or question 2, or it could be the long question. Okay. In any case, whenever you do anything to do with circuits, right, you follow the instructions and you connect it, right? Now, there is a very small chance that even if you check everything is okay, if your meter does not give you a reading, right, the ammeter or voltmeter, of course, you will check your connections. If everything is fine, you cannot be sitting down there like 10, 15 minutes to see what is wrong. Like after 5 minutes, you check everything is okay, still not getting a proper reading, or your reading keeps changing, right? It's okay to put up your hand, right? Guys, don't worry. It could be actually something faulty with the wire itself, right? If you are 100% sure everything is okay, because I know students who actually sit down there for very long thinking that putting up the hand can be an issue, right? So remember that. Yeah, James, you got the value, yeah? How about the rest? Yeah. Okay. So guys, so if you look at this, the gradient calculated. So what do you all get? 0.09, 0.039. The unit is there, second squared per cm. Second squared per cm. Right? So we give it to the 2SF here. Okay, so I just want to highlight this before I pass it to teacher Meng Yi. Okay, yeah, thanks, James. Yeah, the thing is, when it comes to the the SF and DP, I repeat, your raw data follows decimal place. What is raw data? In this case, if you look at this table, the length is a raw data. Time 1 is raw data. Time 2 is raw data. Because you are using an instrument to measure. Ruler, stopwatch, okay, thermometer, all this, whatever you measure is the raw data. It must be consistent in the decimal place. Okay. The process data is the big T and the period and T squared. That is a process data. Technically, the average is also a process data, but the average will follow the DP as of the raw data. Okay, right? So guys, just in case you're wondering, suddenly, do I give to 2? Right? Yeah, Aditya, because the gradient, yes, actually, you see, you can calculate the gradient to 3SF, no problem. But 2SF also based on the data here is fine. Okay, but never exceed more than 3SF. Don't exceed more than 3SF. Okay. So, yeah. Yeah, the lowest SF. Yeah, correct. So, guys, but remember, I repeat this point to you again. The processed value will follow the SF of it will follow that of the raw data. Okay. That one you have to be clear. Okay, now remember your practical is going to be like this. First, for physics, the first 2 questions, 20 marks. the second question will have the planning component. Similar to what I was saying, they will give you a bit of an experiment to do, and then you plan it. The third one is the long one, where you have to come up with a table, plot a graph, calculate gradient, and then they can ask you questions. Okay, what are the precautions, or what do you think can be improved in this experiment? So ultimately, I just want to leave you with this. Read the instructions carefully. That is what is most important. And look at the diagram given to you, right? So one thing is look through your previous like a prelim practical and see where you lost marks and see why you lost marks. And then you'll know what happened, right? Okay, guys, we're done for this part. I think Teacher Mengi will take over, yeah?
Yes. Thanks. People online, can you hear me? You guys hear me online? I just see whether they
Yeah.
I think they can, right? Okay, anyway, let me just introduce myself. I'm Teacher Mini. I think we didn't introduce at the start. Okay, so of course, you can see Teacher Kade is a master teacher for physics. So I'm the master teacher for chemistry and also the head of science in my stretcher. Okay, so we're going to go through the chemistry parts. We don't have a lot of time. Okay, right. So first thing, you know what is the most important thing in your chemistry? Practical, of course, is titration, QA, the most common type of questions being asked. Okay, now when you do a titration, the most important thing is what do you wash them with? You have your burette, you have your pipette, conical flask. What do you wash them with? What do you wash the burette with?
First with is the water, then the solution, and then the
Very good. What do you wash the conical flask with?
Conical flask.
Below the burette. Distilled water. Anything else? Okay, seems like you all know it very well. What do you wash the pipette with, Lucas?
Distilled water and solution.
Okay, good. So you all know all this now. So you must definitely know what you need to wash this apparatus with. Okay. So when you do a titration, you use a pipette to draw out a solution, be it the acid, the alkali, or some other solution, depending on what they give you. Right. Then you put inside the conical flask, which you have only washed with distilled water, right? And you add an indicator. Then that's when you start your titration, right? So when your indicator you add is most likely one of these three. Okay, you don't really have to go and memorize this color. You don't really have to memorize. Did you ask you to memorize? No, right? Okay, because you just need to record observations. All right, you just need to know. Actually, you don't even need to record. You just know its endpoint, then you just take your reading. Okay, so you don't need to record the color. So just for you to know. Okay, so the most commonly used is Mistal orange. Okay, right. So make sure you know what to wash your apparatus with. Now, always for titration question, you must always read your question. What is the two unknowns given to you? Okay, all the information in the question, because later got calculation, right? So you must know, you must go and highlight or circle or underline all the concentration, how much volume do you have used. Okay, all those, please go and underline and circle them. Okay, so we'll look at the calculations later. All right, so if let's say you are still a little bit uncertain on how to do a titration, all right, you can watch this video at your own time. So actually there are a lot of titration videos or other chemistry videos on YouTube. Okay, so please go and find them if you need to. Okay, yeah. Okay, so let's look at this question. So this question, we have hydrated sodium carbonates. Okay, Na2CO3, X number of water molecules. So this is a hydrated salt with X number of water of crystallization. So in this reaction is between sodium carbonate and hydrochloric acid. Okay, so it's an acid carbonate reaction. So you have some information, right? You can see I have 14.65 grams of sodium carbonate. That is the hydrated salt in 1 dm cube of solution. Do you realize this is actually a concentration? Because this is the mass in 1 dm cube. Right, mass in 1 dm cube of solution. Okay, so that is concentration in grams per dm cube. Okay, so that is P. For Q, 0.100 mole per dm cube hydrochloric acid. So all this information you must take note of, because later you will need to use them. Okay, and the rest will be the very standard one. Okay, you prepare 25 cm cube of P. Okay, don't prepare the wrong one. Put inside conical flask. Okay, and do your titration. Now, when you all do your titration, so just some of the things to take note when you put your solution inside the burette. Okay, remember you should pour with a filter so it don't spill all over the place, right? But once you fill it up to the 0 mark, no, sorry, should you fill up to just the 0 mark and stop there? Should you fill up to 0 mark and what should we do?
Use some space.
Leave some space. What do you mean by that? Don't know? Anyone? Do we fill up to the 0 mark and just stop there? Like, do we purposely fill it up to the 0 mark?
Here.
Yeah? Yeah? Why no?
A bit more than this, more than that's some of the solution after them and
Correct. So you should fill up more than a 0. More than a 0. Okay, so let's say this is a burette, right? So of course this is just a shortened one. You should fill up more than a 0. Yes? Yeah, you fill up more than a 0. Why? So that you can flush out. You can turn on the tap, right? Flush it out. Flush out any air bubbles. And then let it be 0. Okay, if you fill up all the way to 0, but you still need to flush out air bubbles, because you cannot forget that step, right? Okay, we need to flush out any air bubbles in the burette. Okay, so you fill up more than 0, and then you flush some of them out. Right? Okay, so let's look at some of these reading. I think we have given you the first reading, right? No? Okay, can you all fill out the first reading? And okay, the first reading we have given you here. So I want you to try to fill up the second and third titration. The first one is quite straightforward. Okay, remember burette, the smaller number is on top, bigger number is below. Okay, so for your practical, it's not just doing the hands-on only. There will be a lot of these data to write. Make sure, okay, your burette reading, how many decimal places you must know. That's why you give you the first column here. Okay, you must always have 2 decimal places for burette reading. Okay. Then you want to double check your answer? Seems like, see, can make careless mistake, right? You must read from the top to bottom, not from the bottom to the top. Read downwards. Then choose your best titration results. Which are your best 2? So usually in the exam, this table is not given to you, right? So you have to draw it out, sketch it quickly. Okay, you don't need to draw it like perfect rectangle, perfect table. Just do a quick sketch, save time. Okay, you don't have so much time in the practical. Okay, so double check your answer. Yeah. Okay, so for the second one, right, the first reading is 10.00. Okay, you see, after the first titration, you will definitely have used up some. And then you'll be left with just 26.80. So you have to top up. So you can top up to any nice number, so maybe 10.00. Okay, try not to top up to a strange number. Okay, but although any number is fine, okay, just make it easy for you to read. So 10.00, and then yeah. So you can see here, this is 36.4. Okay, do not read from bottom to up. This one 37.6, and that's wrong. Okay, so you must read from the top to the bottom. Okay, so that is 36.4. So when you do a subtraction, that is 26.40. And for the third one, okay, it's 26.3. So for the best two titration results, how far away should they be? What's the difference between the two best titration results? How much can we accept? From here, you can see it's just 0.1. Okay, but the maximum we can choose is 0.2 plus minus 0.20. Okay, so definitely do not choose number one where it's at least a 0.40 away. Okay. Yep. All right. So if we have found the two titration result, this will be the average. Okay, average, I don't think you have any issue. Okay, so this is just a plus together and divide by 2. All right, so we'll make use of this volume of Q. Okay, and let's do some calculation for B part 1. So you read through your question again. How do you solve this question? Okay, I give you a few minutes to try this. Think about it. Definitely, you must use the volume of Q, the average volume of Q that you have found out. Okay, so for practical, you do not just have to be good at hands-on activity, your more concept and stoichiometry must also be good. Okay, this triangle is given to you here, so you can refer to it. I think it's not on your paper, in case you are not familiar with the formula. Yes, volume times concentration. So what's the concentration? And then that's when you look at the front and find your concentration. Okay, answer is given to you. So basically you are trying to arrive at this answer and see whether you get it or not. Think that the question is asking for 1 dn cube. In our experiment, we had only used 25 cm cube, but the question is asking for 1 dn cube. So there's one extra step that you might need to take. People online, have you all solved the question? Anyone have solved the question? You solved it? Great. Okay. That's one thing is you must show your full calculation. So at least this one you must show is times 2 to get this. You must show the ratio based on the equation. Other than that, I think the rest are fine. Okay, got it? Did I get it? Yes. Okay, so the first thing we have is the average volume of Q. So we'll use this volume, and the first thing is find out what is the number of moles. Okay, whenever you're stuck in the mole concept question, I always tell my student, first thing is just find number of moles. Okay, so what can we do with this volume? Do we have the concentration? Because concentration times volume gives us the number of moles. So concentration, you can flip to the previous page, is given as 0.1, right? Yes, 0.100. Okay, 0.100. So you multiply it by the volume. So you get the number of moles. Okay, but remember, volume in this case is in cm cubed that we have gotten out of the titration. We must always change to dm cubed. So with this number of moles, this is for Q, but we want to find for T. Okay, so you must do a mole ratio. So you go back to the previous page again, then that is your equation, right? The equation is given to you. Okay, sodium carbonate to hydrochloric acid 1:2. Okay, so acid to carbonate is 2:1. All right. Acid to carbonate is 2:1, so we need to divide by 2. Okay, for the sodium carbonate. Okay, so you must look at the equation to get the mole ratio. So this will give you the number of moles of sodium carbonate in 25 cm cube. Why 25 cm cube? Because this is the one that you have used your pipette to draw out. Okay, this was the one used in the titration, 25 cm cube. But this question is in the end asking for 1 dm cube. Okay, so you need to do some proportion. So in 25 cm cube, we have this number of moles. So what happens when I have 1 dm cube of this solution? So you just do a proportion 1000 over 25 times 1000 over 25. Or you can divide by 25 over 1000. Either way also can. Okay? Right, so for those who got it correct, good job. Okay, make sure you practice on this. Take note of the volume that they want. Okay, because our titration is only 25 cm cube. If they ask for other volumes, you need to do this proportion method. All right. Okay, then follow up the next step. Next question, B part 2. So now, okay, this is just another question, but it has been tested before in the O levels. All right, so when we have now found the number of moles of sodium carbonate in 1 dm cube, this essentially, okay, is mole per dm cube. That's why they ask you to find this. Okay, what you have found in part 1 is 0.0527 moles, but that is in 1 dm cube. So essentially, this is a concentration. Okay, this is a concentration, and it's also, you can use this concentration and the concentration given earlier on. Go back to the front. Yeah. Some more. Okay, so you can see here, at the start, P is a solution containing 14.65 grams of sodium carbonate with some water of crystallization, okay, hydrated sodium carbonate. So this is grams per dm cube. So this is one important information, like I said at the start, this is a concentration. Okay, so this is in grams per dm cube. We have found concentration in mole per dm cube. We can actually derive the MR of these salts. Okay, so MR will be 277.988. Right? So you'll use that and minus away the sodium carbonate. Then you can get your water, the MR of the whole water, okay, and find the value of X. All right. Any questions for this? Okay, go through this process again because they always test on this water of crystallization. All right. Now we move on to the next part. Okay. Now QA. Now, so in your chemistry practical, right, you must always take note of your time, because if you spend too much time doing your titration, then you have less time for your QA. Okay, so we must always have some time management. There might be 2 to 3 activities for you to do. Maybe titration, then followed by QA, and there might be something else for you to check, maybe rate of reaction. Okay, and part of this, there will be some planning questions. So you must plan your time well. Right, so for QA, now before you do anything, always read the question carefully. Just like physics, before you do anything, must read what do they want you to do. Okay? All these tests, you must already know, cation test, anion test, test for gas. Okay, but always remember for your practical, they have given you the QA notes. But of course, by now you should already memorize that, right, for your theory. But in case you have forgotten, okay, they have provided you the QA notes, okay? So you can refer to that. Right. Now, when they give you a few things to use for your reaction, you must always anticipate what the gas is going to be. Okay? So, okay, when you use a test tube, just add a small amount. This small amount, 1 cm cube, you can simply just use a finger, or you can just take a ruler and measure, estimate 1 cm cube, 1 cm depth. Okay, so no need to be exact. Okay, so always predict what gas is going to come out. Okay, you do not just do the test already, see effervescence, then you start looking for your spleen. Then that's too late already. Okay, right. So you see what you are adding into your test tube. If it's a piece of metal, it's very obvious. A metal is always associated with hydrogen. Okay, so you must prepare your lighters, your spleen. You must make sure your Bunsen burner is already ready. Okay, so when you do a reaction, you see effervescence. Now you do not just let the gas escape when the gas is being produced. What can you do to prevent your gas from escaping? What can you do? Put a stopper, possible, or if it's not a very hot setup, you can simply just put your thumb over it, okay, to trap the gas inside. Okay, if it's not heated up, if it is very hot, then you cannot put your thumb. Okay. So for example, if you're testing for ammonia, right? Ammonia, you need to heat it up. You need to warm the setup, and there's no way you're going to put your thumb there and burn your hands, right? Okay, so don't need to do that. Okay, right. So if you're using hydrogen peroxide, that's a hint that you must get ready a spleen as well, because that's to test for oxygen. Okay, what is the observation to test for oxygen? What do you do, and what do you see? Anyone? A glowing spleen, and what will happen to that? You will turn to a fire. It will relight or rekindle. Okay, that's the correct term. So it will not. It will just light up a little bit. Okay, right. If you are adding a powdered solid, most of the time it's carbonate. Okay, especially when it's just some white powder, because most carbonates are white, but not all the time. Okay, so a lot of time you're going to prepare to test for your carbon dioxide. How do you test for that? Of course, a lime water. Okay, you have a delivery tube, and make sure the delivery tube enters the lime water. Okay, right. Ammonia, like I mentioned, we need to move the boiling tube in and out of the Bunsen flame. Okay, it must be heated for ammonia to be produced. Okay, so if you are adding sodium hydroxide, now sodium hydroxide can be used to test for many things, like cations. You use sodium hydroxide. Okay, but to know it's ammonia gas, what's the one thing that you add that is very obvious is to test for ammonia? Sorry?
Litmus paper.
Litmus paper. Yeah, that is, no, I'm saying that how do you know it's going to be ammonia being produced? Smelly. That is when it's already produced. Now, how do you predict that it is going to be produced? That is different from all the other tests. Anyone? Aluminum foil. Okay, not just a piece of metal at the top. When we talk about aluminum foil, there's only one thing. It's nitrate. Okay, and ammonia is likely to be produced. Okay, right. So remember that. All right. When you add so test for cations, test for anions, all this is part of your theory QA also. Okay, so like I said, please refer to the QA notes in your exam. All right. When you test for cations, remember there are 2 steps. You add a few drops first. Write down the observation for the first test. Okay, then you add even more to half the tube. Okay, that will be considered excess. Then you take note of the observation again. Okay, now when you do anion test or other tests where there are no changes, you don't see anything, please write no visible change. Do not write nothing happened. I believe your teachers have told you that many times. Do not write nothing happened because something might have happened, you just don't see that. Okay, so no visible change. Right? Yeah. Move on. Okay, let's look at this. So first thing, now hydrogen peroxide. Hydrogen peroxide is a substance that can actually act as both a OA and a RA, oxidizing agent and reducing agent. Okay, but you know for potassium iodide is a reducing agent. A reducing agent is added to test for an oxidizing agent. Okay, while potassium manganate 7, there's an oxidizing agent is used to test for reducing agent. So this QA, if you see that all these substances are given to you when you do your QA, you know this is a redox reaction. All right, so let's look at show one video there, the first video. You'll write down the observation for me to see, yeah? Let's press control. Yeah. Okay, there's no sound for this, huh? So initially it's colorless. Okay, this color, yeah, you can still see a bit. It's a bit blur on the screen. Okay, but you can see, right? Actually, you can see there's some bubbling. There's a lot of effervescence happening. Okay, and you see what she did? She used a thumb to block, make sure the gas don't escape. Okay. And she did a test for oxygen. So the lighter spleen rekindled. All right. So what exactly happened here? So she added potassium iodide to the hydrogen peroxide. Okay, so the color change is colorless to, okay, in the video she said pale yellow. So it really depends on what you see on the day. By right, in theory, we think that, okay, it turns brown, right? Because we added potassium iodide. So if you really see it's pale yellow or yellow, just write colorless solution turns yellow. Write down the true color that you see. Okay? And there was effervescence. So you realize effervescence, and because there's a gas produced, you test for it. Now, every time you test for a gas, you identify the gas. Don't just simply say effervescence, and then it relights a glowing spleen. Full stop. Stop there. No. You have done your test, so identify what test that is. Okay? Now let's look at the second one. So this is potassium iodide, and you're going to add potassium manganate 7. Okay, what do you think the color will be? Now it is potassium iodide, which is colorless. What do you think after adding potassium manganate 7, what would be observed? Think about it, huh? It's now colorless. After you add potassium manganate 7, what's the color? Anyone want to try? Colorless, which means you don't see anything. It remains as purple to colorless. So potassium, but what will be the final color? colorless. Okay, anyone else got different answer? No? So all things is colorless.
Brown. Online says brown.
Brown? Any other answers online? So we have colorless, we have brown. Why brown? Maybe it could be brown. I2, iodine. So we are adding potassium manganate 7 into potassium iodide. Okay? The potassium manganate 7 is purple in color, right? So purple turns colorless. So the end color is colorless for that. But this is potassium iodide, which is colorless, turns brown. So brown plus colorless is brown. Okay, so it's a mixture of both end, their end color, right? So you see purple drop, now it becomes brown. Because now it's iodine, because of the iodide. Okay, so yeah. Okay, so the potassium, when you use potassium iodide, the product is iodine, I2. Okay, that is the brown color. Okay, you don't really need to know like potassium manganate 7, it turns into which ion, but it's Mn2 plus that contributes to the colorless solution. Okay, but eventually it's brown because of the iodine. Okay, so mix the colorless with brown, so it's still brown. Okay, usual answer. Okay, so you can write this down. Right, so you can see right in test 1, what have we done? Okay, in test 1, we have added hydrogen peroxide to potassium iodide, right? Okay, so potassium iodide is to test for oxidizing agent because itself is a reducing agent. So in this case, the hydrogen peroxide that was added is the oxidizing agent. So remember, when you use reducing agents, you are testing for the opposite. When you're using an oxidizing agent, you are testing for the opposite. Okay, so if they ask you to confirm what it was used for, what is the purpose, what's the role, okay, or what's the observation and what's the conclusion? So the conclusion will be an oxidizing agent was present, for example, okay, if it's unknown solution. Okay, if you add potassium iodide and you see a positive test, so there was an oxidizing agent, right? Because it's used to test for oxidizing agents. Okay. Right, of course, today we are just covering a small part of titration, a small part of QA. Okay, so go back and go and look up on all these again. All right, and if you have any further questions, okay, please chat with us, okay, or your MyStrata teachers. All right, now I hope you all know that we have some Telegram community. So I know it's already at your last stage, but if let's say you want some extra practice, there are still some free materials online for you all to do, especially your theory exam is still on the way. Okay, that's still 1 month plus away. Right, so free materials, you don't lose out. Okay, please access them if you want. All right. So thanks everyone for coming today. I know it was a rainy evening. All right, so thanks for coming out all the way. Yeah. Anything? You all stay nearby? Yeah, that's why you all can come, right? Great. Yeah, so thanks all those online as well. Thanks for joining us today. Thank you. Thank you. Yes. Do I have any questions regarding our practical and any other questions you would like to ask? No? Okay. Yeah, if you all have no questions, you all may leave already. Thank you very much. All those online, thank you. That's all for today's session. Feel free to join our Telegram community. It's all free resources. Okay, thank you.